graph symmetry. Our objective for this video, we want to algebraically determine, we're also going to look at the graph on our graphing calculator, if an equation's graph has symmetry with respect to the y-axis, symmetry with respect to the x-axis, symmetry with respect to the origin, or none of the above. So, in essence, does our graph have any symmetry? Okay, let's take a look at the definitions of these three types of symmetry and how we're going to test for it algebraically. Okay, so a graph has, the graph of an equation is symmetric with respect to the y-axis. So from right side to left side or left side to right side, using the y-axis as a line of symmetry, if for every point xy on the graph, the point negative x comma y is also on the graph. How do we test for this symmetry algebraically? We substitute negative x in for x in the equation, and we see if we get the equivalent equation. Okay, symmetric with respect to the x-axis, which means we're going to be going from top to bottom, and the x-axis is a line of symmetry, or bottom to top. Okay, a graph is symmetric with respect to the x-axis if for every point xy on the graph, the point x negative y is also on the graph. Okay, how do we test for this algebraically? We're going to substitute negative y in for y in the original equation. We may do a bit of math, and we want to see if we can get the equivalent equation. I want to make a note here. We're going to work with functions, okay? And I want to make a note here that graphs that have symmetry with respect to the x-axis are rarely, if ever, functions. So we're not going to do a whole lot with this one other than take a look at it in this video, because these are rarely, if ever, the graphs of functions, and we're dealing with functions. Okay, finally, the origin. The graph of an equation is symmetric with respect to the origin. In other words, you put a tack right in the origin and you can spin it. Okay, if you can spin it and have it land on itself in less than a full turn, it's symmetric with respect to the origin. Mathematically, if for every point xy on the graph, the point negative x negative y is also on the graph. How do we test for origin symmetry algebraically? We substitute negative x in for x and negative y in for y. We'll do a bit of manipulation, we'll do a bit of mathematics to clean it up. And if we get the equivalent equation, that is symmetric with respect to the origin. Okay, a fair amount of math speak in here. I think it'll make a lot more sense as we take a look at it, take a look at the graph on the calculator, and as we do some examples. Suggestion: if you're given a function, and again, we know if we're given a function, we're not going to test it for x for symmetry with respect to the x-axis, okay, because that wouldn't be a function. But if you're given a function, it's generally easier to replace the f of x with a y and then do the math over here, as opposed to carrying an f of x around. Just use a y instead to see it. It just makes life a little bit easier. Okay, example number 1. Algebraically, determine whether the graph of y equals x squared minus 1 is symmetric with respect to the y-axis, again, left to right, the x-axis, again, top to bottom, or the origin, again, tack and spin, or none of the above. Okay, well, let's start off with the y-axis. I'm going to be writing a little smaller here, given space. I did the best I could with space. We got to do 3 of these tests, okay? Well, here's our equation. I'm simply going to copy it down. Y equals x squared minus 1. Now, y-axis symmetry, I'll come back up here. How do I know? I know if I put negative x in for x and I get the same equation, then the graph is symmetric with respect to the y-axis. Okay, so I'll substitute negative x in for x. Okay, y, and I'll use parentheses. If negative x also makes the same equation, if I can get back to this equation by using negative x instead, it is symmetric with respect to the y-axis. Well, negative x times negative x is positive x squared minus 1. I just had to do one brief piece of math. You'll notice that these two are equivalent, and therefore this graph is symmetric with respect to the y-axis. And again, we're going to take a look at this graph on our graphing device in just a second. Let's test the x-axis. Okay, is this graph symmetric with respect to the x-axis? Okay, well, how do we test that mathematically? Well, we substitute negative y in for y, and to see if we get the original equation. Will we get the equation back that we started with? Okay, so I'll start with my original equation, y equals x squared minus 1. I'll substitute negative y in for y. Notice I'm using parentheses. Might seem a little silly, but I always do that. Of course, we know this is just negative y, but I always start there with parentheses so I don't lose negatives. That's what happens to people. People lose negatives in mathematics. Okay, let's do a little simplification. Well, this is obviously just negative y is equal to x squared minus 1. I multiply both sides by negative 1, and I have y equals negative x squared plus 1. Are these two the same? And the answer is nope, they are not equal to one another. So therefore, it is not symmetric with respect to the x-axis. Okay, finally, let's check this for symmetry with respect to the origin. Okay, origin. All right, it's symmetrical with respect to the origin. Okay, how do we test for that? We go right here. We substitute negative x in for x and negative y in for y to see if we get the same equation. We may have to do a little bit of work. We have to do a little bit of math, just a touch of work here and here. But we want to see if we get the identical equation we started with. Okay, let's go back. Let's write the original. Y equals x squared minus 1. Let's substitute negative y in for y and negative x in for x. Again, I use parentheses. Let's do some math. Well, this is just negative y. Negative x times negative x is positive x squared minus 1. Now I'm going to multiply both sides by negative 1, and I get y equals negative x squared plus 1. Okay, well, are these two the same? No, they're not. Those two are not equal. So it is this graph is not symmetric with respect to the origin. Okay, let's take a look at this in our graphing calculator, our graphing device. I think it got out of the way of my lights overhead here. Okay, so I'll turn on my TI. Y equals, I'm going to erase what's in there, and I'm going to put an x squared minus 1 right here. So x squared minus 1, and I'll graph it. And there it is. And you can see clearly left side maps to right side. The line of symmetry of the y-axis, I can use that line of symmetry that matches. There's the y-axis symmetry. Obviously, using this line, this does not map down to this, and this does not map up to that. And again, if I put a tack at the origin and I spin it, I have to go all the way around 360 degrees until the graph lands on itself. So because it takes a full 360, this graph is not symmetric with respect to the origin. it has to land on itself in less than 360 degrees in order to be symmetric with respect to the origin. Okay, let's do a couple of other examples. It's nice to see a variety of possibilities. Okay, let me get my notes together here. I use my notes so I don't make mistakes. I go through this and make notes, so I already have it down. Algebraically determine whether the graph of y equals x cubed is symmetric with respect to the y-axis, the x-axis, the origin, or none of the above. Okay, let's first test the y-axis. Here's the original equation, y equals x cubed. For the y-axis test, I substitute negative x in for x and see if I get the same equation. So I'll put a negative x in there for x, and I'll use parentheses so I do this correctly. Negative x times negative x times negative x is a negative x cubed. And you can see pretty clearly that those two are not equivalent. Okay, so no y-axis symmetry. Okay, let's check the x-axis. I'll write down the original equation. Okay, to test x-axis symmetry, okay, we want to replace y with negative y. Okay, so negative y equals x cubed. And then we know this is negative y equals x cubed. I just use the parentheses so I don't lose negatives. I'll multiply both sides by -1. And I can clearly see that these two are not the same. Y equals x cubed is not the same as y equals negative x cubed. So there is no x-axis symmetry. Let's check the origin. Okay, original equation, y equals x cubed. Let's replace y with negative y and x with negative x. Again, I use parentheses so I don't lose my negatives. Left side's the same thing. The right side, negative x times negative x times negative x is negative x cubed. Multiply both sides by -1 and y equals x cubed. Ha! Look at that. Those two are identical. So it has origin symmetry, symmetric with respect to the origin. Let's take a look. Okay. We can see how this, we'll see this with our graph. Okay, so turn it back on. Y equals, let's get rid of that previous, and let's put in x cubed. And let's graph that. And there's the graph. You can see clearly there's no y-axis symmetry. The right side does not map to the left side and vice versa. You can see there's no x-axis symmetry. There's no, if you were to flip it, if you were to bring the top to the bottom and the bottom to the top, it would not land on itself. But if I put a pin at the origin right here and I spin it, I only have to spin it 180 degrees for it to land back on itself. Okay, 180 degrees, of course, is less than 360 degrees. That's what makes it symmetrical with respect to the origin. If you can put a pin in there and spin it less than a full circle and land on itself, it is symmetric with respect to the origin. Okay, one more example. This one I gave you it in function notation. Algebraically, determine whether the graph of f of x is equal to 2x cubed minus 3x squared minus 11x plus 6 is symmetric with respect to the y-axis, the x-axis, the origin, or none of the above. Okay, well, we'll start off with our y-axis. Okay, my recommendation is, excuse me, it's easier to replace the f of x with a y so you can do the math a little bit easier than carrying around that function notation. So I'll write that down. Y equals 2x cubed minus 3x squared minus 11x. You're going to want to write a little smaller here because I got to do 3 columns. Okay, now when we test for symmetry with respect to the y-axis, we replace the x with a negative x. Okay, here's where those parentheses make a difference. You got to be careful. Replace all x's with negative x's. Okay, now let's do some math. This is negative 2x cubed. Okay, this is x squared minus 3x squared. This is plus 11x plus 6. Well, it's already y equals, so I'm going to compare. And you can see the first term is different, therefore they are not equal. Turns out term 2 is the same, term 3 is the opposite, term 4 is the same. It doesn't matter. It is not the same equation. Okay, so there is no y-axis symmetry. Okay, x-axis. Again, be careful. We're going to use this paper here. Okay, again, I'll replace the f of x with a y. Y equals 2x cubed minus 3x squared minus 11x plus 6. And for x-axis symmetry, I replace the y with a negative y. And the x's are not replaced. Okay, well, this is obviously just negative y. So I'm removing the parentheses. And I'm going to multiply both sides by -1 to get a y equals negative 2x cubed plus 3x squared plus 11x minus 6. You're going to compare those two, and you can see they're the opposite. They're certainly not equal to one another. So there is no x-axis symmetry. Okay, well, is it symmetrical with respect to the origin, our last possibility? Okay, again, as opposed to f of x, I'll write it with a y. 2x cubed minus 3x squared minus 11x plus 6. And now I'm going to substitute negative y in for y and negative x in for x to test for origin symmetry. So using parentheses and watching my paper space in my case, minus 11 times negative x, woo, came close, plus 6. Now let's do some multiplication and some simplification. That's just negative y. This is negative 2 times x cubed. This is minus 3x squared. This is positive 11x, and this is positive 6. Now let's multiply both sides by -1 to get a y equals. So y equals positive 2x cubed plus 3x squared minus 11x minus 6. And now we can compare these two, and they are not equal. The first terms are the same. The second terms are different. The third terms are the same. And the fourth terms are different. So no origin symmetry. So this graph has no symmetry at all. Let's take a look at it on our calculator. Okay. So go back into here, go back to y equals, clear out the prior. I've got kind of a long function. So 2x, make sure I type it in correctly, 2x cubed minus 3x squared minus 11x plus 6. Press graph. Okay, well, there you go. You can certainly see that it's not symmetrical with respect to the y-axis. The left side does not map to the right side does not map to the left. You can see it's not symmetrical with respect to the x-axis. The top does not map to the bottom does not map to the top. And finally, if I put a pin in at the origin, which is just to the left of where it crosses here, right there, it requires a full 360-degree spin to get back on itself. And because it requires a full spin, it is not symmetrical with respect to the origin. Okay, so that's how to do this algebraically. Obviously, it's far easier with a calculator and a graph. A word of warning, and I speak to this a lot. Replace when you're replacing variables with something different, it really makes a difference to use parentheses so you don't lose track of negatives.